My name is Juan Carlos Levigar, and I am doing my final project for machine learning foundations for product managers in Coursera, provided by Duke University. And as part of the final project, I need to create a machine learning model to predict the electrical energy output of a combined cycle power plant. I have 5 minutes max to present the information. The information I will present is the modeling approach, the model building, model evaluation, model interpretation. So I basically need to correctly identify the model and the type of modeling task features to use, and the algorithm. So based on the information we have in this project, the goal was to predict the net hourly electrical energy output. And the data set that they provided was 9,600 approximately observations, environmental readings collected from power plant sensors. And we had ambient temperature, we had exhaust vacuum, ambient pressure, relative humidity, and targeted variable power output in megawatt, so PE. PE is a continuous numerical value. So regression was the most appropriate machine learning approach. So our objective was to find the best model that maximized predictive errors, and supervised learning, because the data set, could they label examples where the actual energy output was known? So with supervised learning, regression was the correct model. And basically, model building, I needed to create more than one model to compare them. So what I did is I used different features in different models to determine if there was any features we could eliminate and what the impact of eliminating features was, or if perhaps maybe these features, there were too many, they were overfitting. So the evaluation metrics that I'm going to provide are the mean absolute error, because it penalizes large variations, large errors. When you deal with energy, you don't want to have large errors because that means blackouts and so on. And R2, because I wanted to make sure that the model was a strong fit to the problem. And then here I'm going to show you the workings to show the model interpretation. First of all, we split the data 80-20%, 80% training, 20% testing. I also randomized the data first, and then I split it. So training data only has 80% of the training data, and then testing data only has the 20% of the testing data. So in training, the first training model we did was creating a training model with all the features, so regression, modeling, analysis. And from doing that, we were able to determine the R squared right away, 0.92969. And then from here, we calculated the absolute error, the residual, and then to be able to get the mean absolute error, which is 3.591196. So that's with the full set of data. We also created a scatter plot, so you could see the data in a scatter plot, which had potential if we had way too many features of overfitting. And then for model number 2, I removed the random RH, just test it out. Feature RH. So we did the same regression model using without RH, one less feature, and we got the mean absolute error again, 3.849, and the R squared of 0.91. Now immediately you could tell that this was going to be less of a strong fit because it was less close to 1, the R squared, and the mean absolute error meant there was more risk for error because the number was higher. And then for training model 3, I remove AP. AP was the feature with the least correlation or the least to PE. The coefficient was the smallest one, and the T-stat was the smallest one. So let's believe that without AP, there might not be much of a difference, and maybe less overfitting. So we remove AP from the features, and ran the regression analysis. Our average was 3.589955, and R square was 0.924436. So in order to verify what that meant, I did a comparison chart here. And the mean absolute value was actually smaller without AP, but the R squared was also smaller, meaning that although perhaps slightly less impact on errors, the R squared, it meant there was less of a strong fit. So the full model was still the best model to use. And so then in the test data, we used the full features to do the testing. So to do the predictive PE, we used the coefficiencies from training model 1. And then then we calculated the absolute error, the residuals, to get the mean absolute error, which is 3.754, which is still pretty good. And then in order to compute the R2 class, we learned that it's the SSR divided by SST, and SST is the actual PE minus the average PE squared, and the SSR is the actual PE minus the predicted PE squared. And then you sum all of the values up from your observations, get a sum, and then to compute, you do K2 minus J2, you do the total sum of SSR divided by the total sum of SST, you get an R2's value of 0.92455. And all that to say that at the end of the day, this was a strong model for this type of problem to solve, with still a very good R squared, so it's still a strong fit to the model. Now, to improve on this model, you could include fine-tuning hyperparameters, testing ensemble models like random forest, or adding more features like fuel prices or so on. So overall, the project for peer review provided the model approach, the model building, model evaluation, the model interpretation. I hope everything was clear. This concludes my presentation, and thank you for watching.